Welcome to the Rock Mechanics demo of the WellCAD Geomechanics workspace. The dataset we use includes a series of raw data, including compressional and shear sonic, as well as density and porosity. We also have some data for the Poisson ratios, the Young's modulus, and the UCS. And we have reference curves for QC purposes, which are the gamma ray and the caliper. And we have a lithology column that is based on the gamma ray using a simple threshold. It separates the shale from the sandy package, which is the main target. The purpose of this demo is to show the geomechanics workspace can calculate the Poisson ratios, the Young's modulus, and the UCS, as well as other rock mechanical parameters. What we will see here is a very common exercise. Users may have core data from the lab, where some of the mechanical parameters have been acquired, which can be used to do core to log reconciliation, dynamic continuous logs versus static, point data, as seen in these dots here. The user will have to go to the geomechanics workspace by selecting this icon, and then you will see this landing site. We are starting from scratch with a new geomechanics workspace. First, we need to select a depth reference. In this case, we have only one type of depth curve, and it refers to the measured depth. We select it. There are two different borehole types that can be selected here: offshore or onshore. In this case, it's an onshore well. As it's an onshore well, we need to enter the air gap, which is 22 meters. The water depth is grayed out because it's not an offshore well. Then the user may select a reference log to create zones by default, but in this case we do not use it. For teaching purposes, we will focus only on the basics and we will not use the zonation, so we only have one zonation that includes the air gap. Here on the right we have the different types of parameters. In this video we will concentrate on the rock mechanical properties. WellCAD has the capability to deliver any of these parameters. But in this exercise, where we only have data for the Poisson ratios, Young's modulus, and UCS, we will concentrate only on these four parameters. There is an option where the user can select these four different tracks together, but for teaching purposes, we will do them one by one. Let's concentrate first on the Poisson ratio calculation. We press OK, and the geomechanics workspace will open with only one track corresponding to that specific Poisson dynamic parameter. We can see different zonations here that correspond to the air gap and the zonations below, the level from 22 meters. We need the raw data, and the user will have to manually import the raw data into the geomechanics workspace. By selecting this button, the log is imported. Alternatively, drag or drop the curves. In this particular scenario, we use the sonic compressional, the shear DTSM, and the porosity and the density. We also use the gamma ray and lithology curves as reference curves. We drag and drop the curves into the mechanics workspace. The imported curves will be displayed to the right. We like to visualize raw data on the left and the output to the right, so we move the logs around. Dynamic track and select a specific zonation. The properties bar is displayed where the input parameters need to be selected, but the user needs to select first the method or empirical formula to be used for the calculations. We use this button to select the method and we'll get default calculations for different types of lithology. We're going to start with the slowness, which is the elastic wave propagation theory equation. It is very common, so we will start with that. We press OK. There is something important that we missed and didn't bring in. which is the core data log with the Poisson ratios. So we drag and drop it. And then we display the two logs on top of each other. This is because we want to compare the output of the calculations with the deterministic values of the lab data. We need to set the same scale for both tracks. So we unselect Auto Scale and set the scale from 0 to 1, matching the Poisson ratio of the core data. For the slowness method, we need to input data for the P slowness and the S slowness. We can use constant values, but in this case we have the DTO and the DTSM. The Geomechanics workspace will generate the outcome that looks like this. And as you can see, the fit is not very good. This means the slowness method is not a good choice in this case. We can try to be more accurate. The target section is the sandstone, so we can create a zonation that goes from this point to this point. When pressing the Shift button on the keyboard, one can create zonation. We can properly fit it up to the top and the bottom of the sandstone. Now that we have the sections set up, we can change parameters in the upper part and the lower part of the shells. So we might want to use a different method. In this case, we select the Abbas method, where we have an empirical equation for the shales. We press OK, and then we get an output on the right. Now we want to propagate this specific method to the other shale sections, which is the lower one. We can press the right bottom and select Apply To, selecting the shales. In this way, the Abbas equation is propagated to all shale sections. The Poisson's ratio using the slowness equation, the elastic propagation theory does not work very well for the sands. We can repeat the process while selecting different formulas or empirical equations. In this case, we select a dedicated equation for the sandstones, that is the Edelman, and press OK. In this case, it requires us to input porosity. It can be a fixed value, in this case 0.2, or we can select the porosity curve that we have. We select it, and this is the output we get, which still is quite different from the core data. In this case, we may have found a situation where the result is quite different from the core data. Therefore, we might want to use the custom editor, which is covered in a separate dedicated video. So let's continue in this video with the geomechanical workflow for rock mechanics. Now we select the Young's modulus and press OK. We have a new log of the Poisson's dynamic ratio E_dyn deployed to the right side of the screen. We use the zonation that we used for Poisson's dynamic log. We right-click, select Copy From, and select Poisson's dynamic log and copy the zonations. We select the sand interval, which is our most important area of interest. And here we select a specific method. We can continue with the elastic propagation method as a default, and that is the slowness and density method. We press OK. It requires P slowness and S slowness as well, and the density, which is another input we have available. This gives us the output in the cyan color, which we may replace in black for better clarity. We can also calculate it in the upper part and the lower part, i.e. in the shales. We can go to the Process tab and select Horsrud method, which is a method specifically for shales. We press OK. We see that it requires p-slowness, which is the DTCO curve, and this is the output. We've got another section of shales, and we can propagate the method by right-clicking to apply the selected lithology, and that was the Young's modulus dynamic. We also want to calculate the static Young's modulus, E_ST, for which we also have some core data, which is here. And we can bring in the Young's statistics modulus track, E_ST, which we overlay with the Young's modulus core data. We now copy the scale from the Young's modulus dynamic to the Young's modulus core data by unselecting autoscale and setting the units to PSI. We can also, by applying the same scales to the Young's statistics modulus, by unselecting autoscale. And we will see the output in the PSI for consistency. Now we have everything together in the same units, so we can also bring in the same zonations by copying them. And we can start the process now. We have different processes that we can use, so let's start with the sandstone as an input, which is this one, and the output is what we get. We can see that there is a large discrepancy. So let's try a new method. Crystaras. Press OK. Unfortunately, it seems even worse. Let's keep the sandstone lacy output and work on the core to log reconciliation by modifying the input, which in this case is the dynamic Young's modulus. To do this, first bring in the shale calculation for the upper and lower part of the borehole. Then select a specific method for the shales, which is the shales lacy. And then we can use the same dynamic Young's modulus, which is this one. We can propagate then to all the shales. Now we've got the output for the sandstone lacy method. Now let's work on the input, which is the dynamic Young's modulus. So let's try and apply another parameter. For instance, we can use the Edelman, which works for porosity, we can see it gets a bit better. Still not good enough, but we can keep it as such for now. We can come back later and see how the UCS method compares with this core to log reconciliation, but at the moment we do not have the UCS yet. Let's calculate it. In the next step, we go to Insert New Parameter and select UCS. And then we will have a new track. We can add the UCS core data that's also available to us. Let's put it in the same track. We can start by creating the same zonations for the UCS calculations by copying them. We do not want to use autoscale for this case, and we want to have the results in PSI. The UCS core data goes from 0 to 15,000 PSI, so we put the UCS on the same scale. Now let's start with the calculation. Let's zoom in a bit more in the area of characterization for a better view, because we are going to start to play with the 3 different parameters that we want to calculate. So let's select the method for the UCS. We want to start with a Freiburg. Now that requires the DTCO. The result is not good, so we repeat the process until the user is happy. Now let's consider the Chang method, which looks better. So let's keep it, as it shows the best core to log reconciliation possible. Now let's bring a method for the shales. We have a lot of shale methods here. We can use the Horsrud method, the one using the P slowness only. Between the input here, and then we extend it to the lower shale section. Now we can select the UCS that we just calculated here to calibrate the Young's modulus static here, where some sections are not quite right. We can come to the dynamic Young's modulus, which is using the Edelman equation for sandstones, and we can select the Sabatakis equation that uses the UCS that we just calculated. We select the UCS log and check this. We have a nice fitting except perhaps at this point. The static Young's modulus is then properly calibrated and the UCS is properly calibrated. So the only one which may do a better job is the Poisson dynamic output. This will be done in another video to show how to use the custom equation editor, which is one of the most important features included in this Geomechanics workspace in WellCAD. So once we finish this, and if we are satisfied with the output of the Geomechanics workspace, we can go to the export log option to visualize everything in a nice borehole view. We select the logs that we want to export and we press OK. That will give us these 3 nice logs, which we can see how they fit in this borehole view. That can be used for printing reports, etc. There will be a few things that we probably need to edit and correct, like these big spikes here and here, and that can be part of the editing that we can perform at a later stage. Thank you for your time, and we will see you in the next video.